In our last lesson, we learned that we could compute the area of a surface S that is a parameterized surface that we have a vector function r of u comma v with by finding the double integral over S of d sigma. And we learned that differential operator sigma was equal to the magnitude of the cross product of the partials of r with respect to u and v, du dv. In this video, I would like to define a surface integral. So I want to consider a parameterized surface, S. And so I'm mapping a uv into S using this parameterized function R. I want to imagine a partition in the domain, and the vector function R would then map that into a partition of S. In each one of these little regions, which aren't necessarily rectangular, I want to imagine that I take a sample point. I've highlighted one of the regions here because I want to imagine that point as an xk, yk, zk. And of course, each one of those little regions would have that point in there. Well, I could imagine this Riemann sum obtained by plugging that into a function on 3 variables. So let g of x, y, z be a function on 3 variables. And then times the area of one of those little regions, and that was a delta sigma from our last lesson. So I could imagine constructing that Riemann sum in the same way I've constructed many, many other Riemann sums, and maybe the idea here is I'm trying to find an average value of temperature across a sphere, and g here is a temperature function. So I find the temperature for one spot in each little region, I multiply that by the area, I add all those things together, and then I divide out the area at the end, the whole area of S that we learned how to compute in our last lesson. And of course, right now, this is a Riemann sum, and it would just be an approximation. To make it be the actual value, I need to take a limit as n approaches infinity. And this becomes my definition of a surface integral. This is the double integral of S over S of g of x, y, z d sigma. And so it's much like the area integrals we were doing before, but now we just have an integrand. And of course, this isn't very well a computation formula, but we can turn it into a computational formula just by substituting in the vector path and using what we know about d sigma. So to evaluate a surface integral, we would simply do this. We'd replace x, y, and z with the components of R. So I'm going to think of those as x comma uv, y of uv, z of uv. Just the components of my parameterized function. And then times d sigma. Well, we know that is the cross product magnitude of the partials with respect to u and v, du, dv. And of course, we could change that order around depending on our region and how we wanted to integrate it. And of course, that should be in line over here, and I ran out of room. Well, let's see if we can just work through an example. So I'm asked to evaluate the surface integral over a surface S of a function g of x d sigma. The function we're given is just g of x, y, z equals the z coordinate. And the surface is y squared plus z squared equals 4, which is a cylinder. I'm told that z is bigger than or equal to 0, and x is between 1 and 4. So my first job will be to parameterize that surface, and we'll go from there. So first thing I'm going to do is I'm going to try to imagine what this surface is doing. So let's look at an x, y, z space. And I'm told that z is bigger than 0, so I only need the upper half space. And I know x is between 1 and 4, so I don't need to graph anything behind the yz plane either. All right, and here on the x-axis, let's see, 1, 2, 3, 4. My surface will live between 1 and 4. It's positive. 1, 2, 1, 2. Let's see here. If I was just looking in the yz plane, where x equals 0, that would be a circle of radius 2 centered at the origin. So if I was thinking about that, I'd get a circle here, but now I realize that I need to be out here x equals 1. Well, this is a cylinder, so I'm just looking for the part of the cylinder that lies between x equals 1 and x equals 4, so I can imagine dragging that circle across. And we're just going to get this little half right circular cylinder. That's the surface S. And so now our job is to parameterize S. Well, all I know about x is that it's between 1 and 4, so I'm just going to call x x. And then I'm going to use what I know about polar coordinates. So I'm going to let this be a parameterization of the variables x and theta, and the x-coordinate is just going to be x, and I know that x is between 1 and 4. Now for the y and z coordinates, I'm going to imagine I'm parameterizing a circle in the plane. It's just in the y-z plane, a circle of radius 2. Well, in drawing it like this, I'm imagining that the y-axis is what I usually think about the x-axis being, and then the z-axis is y. So I'm going to think about y as being an r cosine theta and z as being an r sine theta. And I'm just going to parameterize the circle, and what I know about the circle is it always has a radius of 2. So that's a 2 cosine theta and a 2 sine theta. All right, and I'm only graphing the top half, so I need theta to be between 0 and 1 pi. And now I've parameterized my surface. Okay, so I'm ready to set up my double integral. Well, I just take the z-coordinate. When I substitute in g of x, y, z, I just get the z-coordinate, so I get 2 sine theta. And then I'm going to need the cross product of the two partials in magnitude, and then dx d theta, or d theta dx, however we feel like doing it when we get there. All right, so let's find these partials and take a cross product. So I'll do that on a different board. So the vector function that generates my surface is x 2 cosine theta 2 sine theta. We need to find two partials. A partial with respect to x, well, that's going to be 1, 0, 0. And a partial with respect to theta. And that's going to be 0 minus 2 sine theta and 2 cosine theta. So just pretty easy partials to deal with. And now we need to evaluate a cross product. And after that, we'll find its magnitude. So our x cross our theta. Shouldn't be too hard of a cross product to take with all these zeros in this determinant. So if I go to compute the I part, I get 0. All right, if I go to compute the j component, let's see, I get 2 cosine theta, that'd be minus 2 cosine theta j. And when I go compute the k component, I get another minus 2, now sine theta k. So there is our x cross our theta. When I find the magnitude, I square these things and take a square root. But if I think about it, those are parametric equations of a circle of radius 2. So when I find the magnitude of this cross product, I just get 2. So now we can return to our double integral. Because now I know this is 2. And I've already found bounds. These are from 1 to 4 and 0 to pi, and so is this one, honestly. So get those bounds in there. All right, pretty easy double integral to evaluate. If I integrate with respect to x, I would get 4x sine theta. Evaluated from 1 to 4, well, you can fill in the details, but what you get is 12 sine theta. Take an antiderivative with respect to theta now, and we'll get minus 12 cosine theta evaluated from 0 to pi. Well, you plug in the pi, you're going to get out 12. And you plug in 0, and you're going to get minus a negative 12. So plus 12 more is 24. And we have found a surface integral.